Okay, another thing I did on the graph, which is very similar to what I did up here, I drew horizontal lines for the maximum voltage, horizontal line for the minimum voltage. I did that for the V sub R voltage. Okay, so this distance represents the radius of the green circle. Now the graph is a little smaller. Scale of the graph is vertical scale of the graph is a little smaller than the scale of the circle, but everything's in a half decent relative scale. We see that V sub R is bigger than the V sub R vector is bigger than the V sub C vector, which is bigger than the V sub L vector because of these numbers here. So right there is our V sub R. That's the amplitude of our resistor voltage. Somewhat less than that, 8/10 of that, 8/10 of this. Here's our maximum capacitor voltage. This is the amplitude then of the capacitor voltage. And then we have about, half of that would be the amplitude of the inductor voltage, because of course the inductive reactance is half that of the capacitor. Okay? So I've got those amplitudes clearly indicated. The V sub L is going to run between the purple lines, the V sub C between the orange lines, and the V sub R between the green lines. Okay, well, if I now, and my 90-degree angle didn't come out exactly 90 degrees, so I had to fudge things a little bit. If I add the V sub L, V sub C, and V sub R vectors, not the projections down here, those don't add, those are out of phase, okay? If I add the vectors though, they add to a V net vector. And it's really easy to visualize adding them. The VL and V sub C are going to be along the same line and in opposite directions. So the total of those two vectors will just be in the direction of whichever is greater, and in a proportion that depends on how long these vectors are. In this case, this vector is half as long as this one, so that when we add the two, we get a vector that's half as long as this one in the direction of the bigger. Then to this vector, we add the V sub R. Now, I didn't get my 90 degrees very good here, so when I try to draw a rectangle up here, which is what this is going to be, because you have 90 degrees between here and here. If I draw my parallelogram, it's going to be a rectangle, and the hypotenuse is going to be a little bit longer than V sub R. Now, when the first time I drew it, I actually got something that's a little shorter than V sub R, and that's ridiculous. So I just fudged it, made V sub net a little longer. If you do this accurately, this is going to be the hypotenuse of a triangle, of which this is one leg. This can't be shorter than this. And here's the leg. It's not all that long, so this isn't going to be all that much longer. The V net's not going to be all that much longer than VR, but it's certainly going to be longer. So I drew it like this. And now on my picture, I've got my maximum V net that's going to occur on this line. This a little further from the axis than the green line, because of course the V net amplitude is a little greater than the V sub R amplitude. I didn't draw the negative of this because I don't have any board space down there. So we can't actually draw the curve all the way down to its minimum, but we can see that V sub net lies a little bit behind V sub R. Not only that, but you know what these numbers are, so you've got to be able to figure out the angle between V sub net and V sub R. Okay, well, I mean, it's very simple. If this is 10 units, well, this is 8 units and this is 4 units, so when I add these two, that component is going to be 4 units, this is going to be 10 units. Okay? So this angle is going to be, well, within this triangle. This angle has opposite side here, adjacent side here. This angle is going to be the arctangent of 4/10. Now we're going to be behind V sub R by the arctangent of 4/10. But we can easily calculate that. So that's very easy to calculate, and calculate that. Whatever numbers I give you, you should be able to calculate that easily. Okay. Now, we see that V net is going to peak a little bit later than V sub r. So I drew two x's here to show where V sub net might peak. And then, of course, it's going to hit a valley halfway between the two peaks. So there's going to be a valley down a little bit below this tiny arrow, red arrow that I'm drawing here. And it's going to be 0 halfway between here and here. So it's going to hit 0 a little bit to the right of this point. So we're going to hit 0, whatever this distance is, to the right of this point where these two intersect. Okay? And then it's going to come back up through 0. Now, I don't think I'm drawing out at the right point. Okay, I just kind of made a mental jump that isn't justified. Okay? It's going to hit 0 a little bit to the left of where V sub r hits 0. And V sub r is hitting 0 here, so it's going to actually be a little bit to the left of this point, and a little bit to the left of this point. Anyhow, we can then draw our net voltage. Now it's going to hit its minimum here, and I don't go low enough on the graph to hit that, and I'm kind of fudging here. So I'm not doing a very good job of drawing that curve right, but you can draw your own and improve. Shouldn't be difficult to improve in what I just did. And that's going to be your actual net voltage drop around the circuit. So this would be the curve for whatever voltage is driving this circuit. Now, I gave you a number of different scenarios. Okay, I gave you two reactances and a voltage, a resistance. So you can draw your phasor diagram. Then I ask, what happens if I change omega? What happens if omega gets bigger? Well, our capacitor reactance is going to get smaller. So our capacitor circle is going to get smaller, but our inductive reactance is going to get bigger because you got a bigger omega. Omega L is going to be bigger. So that the inductive reactance circle is going to grow. It might actually get bigger than the circle for the capacitive reactance. Well, that's going to change the amplitudes on this graph. It's going to change the sizes of these circles. And it's also going to change the direction of V net. For example, if VL gets bigger than V sub C, then if I add the VL and the V sub C, it's going to be in this direction, and now my V net is going to be ahead of VR, which is going to shift the graph of my V net somewhat to the left. It can also affect and will affect the magnitude of V net. So we have to start by calculating these quantities in terms of whatever I say happens to omega, and then drawing the appropriate picture and constructing the appropriate graph. Now, it doesn't take long to do this once you've done a few, but you've got to do a few. And there are other connections that arise, but if you can get this picture and this process, you're doing pretty well. And then we'll be able to build on that by bringing that back into the context of our differential equations. And we can also explain why we do all this stuff in the complex plane, because really you can interpret this as a complex plane, real, imaginary, and our projection here is the real part of our solution. And if you take differential equations, that ought to really get your attention. Okay, well, we have to do this. So I do expect you to work on this between now and Monday. You got 5 days, plenty of time to work on it.